Hey, welcome back. Today we're going to be talking about the magnetic force. And so maybe you are a physics student who needs to know more about how the magnetic force works, how to measure it, how to do a basic calculation with it, what the variables mean, and so on. That's what we're going to be talking about here. We're also going to be going over Ampere's law a little bit. And lastly, we're going to be talking about the right-hand rule for the magnetic force. So hopefully you have felt the repulsion or attraction of two different magnets, depending on how they're oriented together. So you know that there is a magnetic force. You've felt it before almost certainly. And it's actually really important. It's not just for kids' toys or whatever. It actually is a necessary component in motors and generators. So we'll be talking in more detail about that as the course proceeds. But I do want you to think about if a charged particle is going to move through a magnetic field. Like we have charged particles coming at us in something called the solar winds from the sun. And these particles come towards the Earth moving very, very fast. And when they interact with the magnetic field of the Earth, they can give off these amazing light displays. And the physics is complex, but the basics of it is if you have a charged particle that moves through a magnetic field, there is a force that is put on that charged particle. So a charged particle could be like an electron or a proton or something like that. And so to talk a little bit more about that, if that charged particle is going to move through a magnetic field perpendicular to the magnetic field that's represented by the B value right here, then as it moves through, it will have a maximum amount of force. So it will be deflected in one direction. We'll talk about what directions those are in a moment. And we could say if the field is off at an angle so that it is not perpendicular to the motion of the charged particle, there's going to be less of a force and less of a deflection, all things being equal. And it actually turns out that if the particle is moving in the exact same direction as the magnetic field itself, then there is actually no force on the charged particle. Alright, so let's go ahead and see how to apply these equations and think through them. And so first of all, the magnetic force equation right here is going to be the force on a charged particle that moves through a magnetic field. Kind of like we were talking about earlier, if we have charged particles coming in from the sun, those particles are going to be deflected because there's a force that's going to be on them as they go through the magnetic field of the Earth. And so this is going to be our equation for this. This is the charge of the charged particle. This is the speed of how fast they're moving. This is the magnetic field that they are passing through. And this is the angle between the charged particle as it comes in with respect to the magnetic field itself. So if it was at 90 degrees, the sine of 90 degrees would be 1. And if it's less than that, then it will be less as well. And if it's not 90 degrees, if it's less than that, then it will be less of a force. If the angle at which the particle came in is exactly the same as the magnetic field itself, then the difference between them would be 0. Well, the sine of 0 is going to be 0. So that goes back to the image I had just shown you a moment ago. All right, well, based on this, we can actually solve or isolate for the magnetic field of the Earth. And this is what it is. So you could say the magnetic force that's going to be experienced divided by the charge that's experiencing it times the speed at which it's going through the fields. Now, we need a new unit, and so the new unit that we're going to have is going to be a Tesla, where we measure the strength of the magnetic field in Teslas. It's a derived unit, and so if we assume kind of 1 for the newtons of the force up here and 1 coulomb of charge, and it's moving at 1 meter per second, then you would end up with 1 Tesla. Think about what the strength of the magnetic field is, and we do need a unit to be able to talk about it. This is a picture of Nikola Tesla, by the way. All right, there's one more equation we need to briefly talk about, and that's Ampere's law over here, and this is the magnetic field created by the current in a wire. And so this is called the permeability of free space over here, this mu naught. And so it's like a special constant of the universe, and you can plug it in over here. So the magnetic fields that's created by a current in the wire depends on this constant times the current in the wire divided by 2 pi times the distance between the point in space and the wire itself that's carrying the current. Alright, and all of this is talking about things in 3 dimensions again, so we need to go back and use another right-hand rule to understand what's going on here. So let's go ahead and do that. So first of all, This is the right-hand rule for the magnetic force. This I value right here has to do with the currents. This B represents the magnetic fields, and this F over here represents the force. The way you can remember this is to think of a slap having a force coming straight out of the hands, and you can flick your thumb from your fingers, moving it out, and think about motion going that way, the motion of the particles or the motion of the charge as the current moves in the direction of the thumb, and your fingers will point in the same direction as the magnetic fields. And notice this is actually just a modified version of the previous right-hand rule that we learned, where instead of we're curling our fingers around the wire, we're doing a flat palm, but the fingers still represent the magnetic fields, and the thumb still points in the same direction as the current itself, just like before. And this is all based on the concept that we're going to be using a positively charged object. So if you have positive charges moving across the conductor, as if we were assuming conventional current, this is actually not true, but it is the default that we assume when we're doing stuff in electricity and magnetism, is we assume we're dealing with positively charged objects. In reality, most of the time it's the electrons that are going to be flowing across the surface of a conductor. So one very important thing we need to note here is that this right-hand rule works if you're talking about a positively charged object, but if the object is negative, then you need to make the direction of the force to be reversed, so the opposite direction. So let's go ahead and see how to apply this. So here we go with a problem. It says a uniform 1.8 Tesla magnetic field points north. Alright, so I tried to draw the cardinal directions. Imagine that this is kind of flat. This arrow right here is coming out towards you. I can only do so much in Google Slides to try to draw this in a three-dimensional way, but imagine this S is coming out towards you, the north is moving away from you into the screen itself. Alright, so the field is pointing to the north, into the screen, you could say. Alright, so it says if an electron with a charge here moves vertically downwards towards the ground, so it's going to be moving this way towards the ground with a speed given through this field, what force, magnitude, and direction will act on it? Alright, so first of all, we're just going to go ahead and plug in our numbers here. The numbers are pretty straightforward, not that tough to work with, and we do our best here to avoid little mistakes that'll throw off the entire problem. And that's going to be our answer. Notice our answer is negative, and that's a clue that something else is going on. Think about, why did this answer come out to be negative? Well, it came out to be negative because we're dealing with an electron. Remember that we said that this force, the direction of the force, which we still have to figure out, the direction of the force is based on a positively charged object. So we'll figure it out for a positively charged object, and then we'll do the reverse direction. So let's think about this. You would point your thumb in the direction of the motion of the charged particle. This says I, it's being covered up here. So if you take your right hand, point it downwards, and your fingers are going to go towards the north. That means into the screen that you're looking at right now. So point your thumb downwards of your right hand, your fingers are going into the screen, and your palm represents the force, kind of like a slap. What direction is the force? Well, the direction of the force is going to be to the east. But that would be for a positively charged object. For a negatively charged object, what would be the direction of the force? Well, the direction of the force would be towards the west. So it's going to be the same value, but towards the west is going to be the direction that this electron is going to experience a force. Alright, so hopefully that was helpful. If you have any comments down below, let me know. I'm going to be doing lessons on this entire unit and the entire year of physics, and I hope you all have a great day. Take care.